blinding flash of light with an awesome amount of power. Incredibly, a typical star generates the equivalent energy of billions of hydrogen bombs every second of its existence.
The objects that populate the universe, the beasts and creatures that live out there, are rather remarkable, and they tell a wonderful story about how the universe has evolved.
Our human lives are so short compared to the evolution of a star. We can't see any evolution taking place. So it's really hard to believe at first that the stars really are changing, that they really are evolving.
Through an extraordinary chain of events, these beautiful night lights of the universe create the stellar power that shapes their lives.
A star is a self-gravitating sphere of gas that radiates energy. Now let's examine what that means. The self-gravitating part means that it retains its own shape. It's not deformable very easily. It doesn't flow into some other shape. The next part of the definition is an object which radiates energy. Stars have to radiate energy from their surface. And that means they have to generate energy either by nuclear reactions, by gravitational contraction. In some way, they have to be generating energy inside.
The question then, though, is where does this energy come from? Because clearly stars are leaking energy all the time. When you look at the sun, that's obvious. So somewhere there's got to be an energy source that's replenishing the energy that's leaking out.
Surprisingly, the answer lies in the smallest particles, atomic nuclei.
The energy involved in nuclei is really quite large. Whenever a nucleus changes from one element to another, energy differences are involved, which are quite substantial. One of them is to build heavier nuclei, and this is what happens inside of a star like the Sun. This is called nuclear fusion.
There are lots of different nuclear reactions. First is the proton-proton chain, also known as the PP chain. In this process, 4 protons are mashed together into a helium atom, and a large amount of energy is liberated. So the first nuclear reaction has to be, you put 2 protons together, 1 hydrogen atom with a second one, and you make deuterium. And the second nuclear reaction, you take the deuterium and you put another proton on it, and you make helium-3. The next reaction is 2 helium-3s slammed together, produce helium-4, and there's 2 extra protons left over. Now you could say, why don't you just take 4 protons and slam them together and make a helium-4 all in one shot? But think of the probabilities. These guys have to get very close together to interact. And the probability that you could get 4 protons that close together at one moment in time, that's very short because they're all flying around in this gas.
Nuclear fusion requires that the repulsive force of the nuclei, which both have the same charge, both are positive charged, has to be overcome. And that's overcome by means of the high velocity of the impacting particles. So these reactions can't take place unless the particles are moving very quickly because they're quite hot, and those conditions are found in the centers of stars.
So during the proton-proton chain, hydrogen nuclei successively collide to form helium. In the process, a tiny portion of mass is converted to energy in the form of gamma rays, positrons, neutrinos.
And what one finds is that the helium that results weighs slightly less than the reactant hydrogen. In other words, a little bit of the mass is no longer there. And what's happened is that the mass has been converted via a very famous equation, E equals mc squared, to pure energy. And so that's what powers the sun. The hydrogen is being converted into helium, and a little of the mass in that process is being converted to pure energy.
The immense power of the stars has also sparked the imagination of scientists.
People have dreams of achieving nuclear fusion on Earth. And they want to do that because they see it as a cheap source of energy. They see it as environmentally non-polluting source of energy. They see it as a solution to the energy problems. But there are immense technical difficulties to achieving that goal. The first is the physical conditions that you have to achieve in the reactor. You want nuclear reactions to occur. That means you have to have very high temperatures. You can't take a 20 million degree gas and just put it in a vessel. The walls will melt instantly. So something has to confine the gas. And a very strong magnetic field of proper design could do that. The prototype for that is the tokamak reactor at Princeton. The second design is one where very strong lasers shine on pellets of hydrogen and for very short times and try to ignite them. And that design is the Shiva design of the Lawrence Livermore National Labs near Berkeley. Neither of these designs has achieved practical demonstration of results. There is no case where the energy out through the reactions is greater than the amount of energy that you had to put in to heat everything up. It's these engineering complications which make the achievement of fusion on Earth extremely difficult.
So, what has thus far proven impossible to create on Earth comes naturally to the stars, or at least our best inferences tell us.
We have never visited a star. We've never sent a probe even into the center of the sun. We need a description of the interior of a star. And the only way to achieve that, since we can't measure the properties of the interior of any star, is to create it out of theory. So we take our theoretical understanding of the laws of physics, apply it to the stellar interior, and produce what's called a model for the star.
We don't actually build something out of sticks or clay or something like that, but we build it out of numbers that we compute in with a numerical computer, like actually a personal computer like you have it, like many people have at home, has the capability to calculate a model of a star.
This model is basically a tabulation of the physical properties as a function of depth in the star. The pressure, the temperature, the number density, the abundance of hydrogen, the burning rates, everything is tabulated as a function of depth. And one can use the model, once it's been calculated, to make predictions about the stellar luminosity, about the rate at which the star will age, that could only be done with the aid of such a detailed prediction for this interior. And so one runs these solutions for different time steps. You start when the star is young and it's all hydrogen, and then in the next model maybe the center has burned up a little hydrogen, and in the next model the star is a little bit older and it's burned up still more hydrogen, and eventually it becomes a red giant, etc. And so you have these grids of models that predict the observable stellar characteristics.
While computer models provide theoretical understanding of a star's interior, they do not provide direct evidence. For that, we must look deep underground. Here in buried observatories, astronomers search for neutrinos, subatomic particles created in the core of the sun. Neutrinos carry secrets of a star's inner workings. Yet, the particles have puzzled scientists for decades.
It is quite surprising that there is still a puzzle associated with the nearest star to Earth, which is basically the sun. And the puzzle is called the solar neutrino problem. We can predict how large a flux of neutrinos will be emitted from the sun due to nuclear reactions that provide the solar luminosity. And then we can attempt to actually measure the flux of neutrinos coming from the sun. And in fact, this experiment was already done back in the 60s. And the flux that was deduced was smaller by at least a factor of 2 or 3 than the prediction, the theoretical prediction back then. And this discrepancy persisted over the last 30 years or so.
A neutrino is one of the fundamental elementary particles. It happens to be the most weakly interacting of all particles. It just goes whizzing right through us all the time. In fact, every cubic centimeter, the tip of our finger, right now has approximately 400 neutrinos whizzing through it at any instant, and yet we don't notice them. Because they go through everything, they turn out to be an important probe of the universe. They end up in astrophysics in cosmology because they came out of the Big Bang. They're important in supernovae because they're the thing that came out of the core of an exploding star. And they're important in our sun. They're produced in the nuclear reactions that generate the energy for our sun.
Photons, generated in the core of a star, take up to 1 million years to work their way through the dense gases to the surface. Neutrinos, on the other hand, stream out unimpeded, giving us an immediate indication of the amount of nuclear fusion at the solar core.
The neutrino problem is a fascinating one, almost as much a problem for nuclear physicists as for solar physicists. Every other measurement we've made tells us that our models are right. The kind of science that determines how hot the sun is at the center, what the pressure is very straightforward and sensible and simple science that is highly unlikely to be wrong. The only problem was when we tried to detect neutrinos. Now, neutrinos are very hard to detect.
The solar neutrino series of experiments has been trying to find those neutrinos from our sun. These experiments tend to be built deep underground to shield them from everything else, because by going underground you can stop all the other things like light from getting to the detector, cosmic rays from getting to the detector, and the only other thing that can get down there would be the neutrinos. For example, there's an experiment in the Homestake gold mine in Leeds, South Dakota, that's made out of cleaning fluid. Huge amount of cleaning fluid deep underground. There's chlorine in cleaning fluid. When chlorine gets hit by a neutrino, every now and then, very rarely, out of this huge amount of chlorine, a few atoms will get converted to argon, a gas. The gas then can be bubbled out of the chlorine, and then the gas can be detected, and you can see how many neutrinos have been captured by the chlorine. That experiment has been going on now for almost 25 years. There are 2 new experiments that, instead of using chlorine, use gallium. When gallium is hit by a neutrino, it converts to germanium. The germanium can then be detected. Another class of experiment is one where the neutrinos, instead of causing a chemical conversion, actually bump into the electrons in the material and cause the electrons to bounce out. This is an experiment that's been done in Japan. The mine has in it, deep underground, a big tank of water. When an electron is hit by a neutrino in the water, it causes the electron to move very fast. People see that fast-moving electron, they can tell how many neutrinos have hit. All of these experiments, the chlorine experiment, the gallium experiments, 2 of them, and the Japanese electron experiment, have all detected neutrinos from the sun. But all of them have detected a little bit fewer neutrinos than what we theorists thought should have been there.
Well, it's still another uncertainty why we don't measure the right number of solar neutrinos, or the number we expect theoretically. There could be a number of possible causes. Either the measurements were done wrong, which we think is unlikely. Maybe the sun, the solar interior, is not behaving the way we think it is. We don't think it's that either. The other thing is the neutrinos aren't quite what we thought they were.
There are 2 classes of explanation. One is that the neutrinos themselves are changing between their emission from the center of the sun and when they get to Earth, in which case then we've learned something new about fundamental neutrino physics. And this would be a great breakthrough in physics itself, because we would learn something about this elementary particle that we didn't know before. And so in that case, an astrophysical experiment would have taught us about basic particle physics. Another explanation, though, is just that the center of the sun is maybe slightly cooler than what we had estimated. It turns out that that latter explanation has almost no effect anyplace else, because the degree of coolness that we're talking about is so small that it's negligible in terms of its impact in other areas of astronomy. The problem with that explanation is it cannot fit all of the neutrino experiments simultaneously. If that is the right explanation, one of the neutrino experiments would have to be wrong. In fact, the one that would have to be wrong would be the chlorine experiment, the oldest one. So if the chlorine experiment is right, as well as all the other experiments being right, it tends to force us to talk about new neutrino physics.
As we learn more about the physics of stars, we're able to refine our models of stellar structure and make more accurate predictions, not only about how stars work, but how they live and die.
Okay, let's take a look at it now.
Each night, astronomers observe countless stars. Most fall within a well-defined range called the main sequence, a prolonged phase where the star's temperature and brightness change very little.
The theory of stellar structure tells us that a star is a ball of gas that is balanced between two forces. Gravity is trying to make the star collapse in on itself. But at the same time, the energy flowing out of the center of the star, that energy flowing outward is trying to make the star expand, trying to make it explode. And the star is balanced between those two forces.
The stability of main sequence stars is guaranteed by the fact that the nuclear reaction rates are so temperature sensitive. If one perturbs a layer, if you try to heat it up a little bit, then the nuclear reaction rates go way up. You might increase the temperature by 5%, but the energy generated will go up by a factor of 2, 3, 4, 5. All that energy escapes out from the star, and it pushes the layer back out. And so the layer then cools. And when it cools back down, the energy generation rates fall back to their original value and stability is restored. It's like a thermostat that regulates the temperature and the structure of the star based on the properties of the nuclear energy generation rates.
We observe that massive stars, stars that contain a lot of matter, produce a lot of energy, and we say they're luminous. We observe that stars that have little mass have low luminosities. So there's a relationship between the mass of a star and its luminosity. That's an observational fact.
These relationships apply because it's the same sequence of physical laws that apply to all stars. There are both theoretical mass luminosity laws, which are based on the predictions of stellar models, and there are empirical ones based on our observation of stars in the sky.
Now we can understand the observed mass-luminosity relation because massive stars have a lot of mass, a lot of gravity, and that means they have a lot of weight pressing inward. And that means they need a lot of energy flowing outward to support that weight. So massive stars have to have a high energy flow, and when that energy gets to the surface, it makes them very luminous. Low-mass stars don't have very much mass, don't have very much gravity, don't have very much weight to support. They don't have very much weight to support, they don't need a high flow of energy out of the star, and that means they don't have to be very luminous.
The upper limit, the most massive star that can form today with the amount of metals that the materials stars are made out of contain, is somewhere between 50 and 100 times the mass of the sun. If the star gets too massive, the radiation pouring out of the center of the star provides so much pressure pushing outward that it actually lifts the outer part of the star off and prevents the star from getting bigger than a certain limit.
We do know that if you took a 1,000 solar mass cloud and tried to collapse it down into one star, the star would be so unstable it would essentially blow itself up immediately. So that's why we don't see really high mass stars. Now on the other end of things, that is at the low mass end of things, we are looking for objects called brown dwarfs, which would be so small in mass that they aren't really fully stars. They would never be able to burn hydrogen in their core and get onto the main sequence.
A brown dwarf can best be described in reference to regular stars. Our sun is a star with one solar mass whose luminosity from the surface is balanced by thermonuclear burning in its core. A brown dwarf is an object whose mass is insufficient to burn thermonuclear fuel at the center to compensate for its losses. So it will form from the interstellar medium as a regular star would, but it would not stabilize on the main sequence, the hydrogen-burning main sequence, and it would cool off like a dying ember over the billions of years of its evolution.
People have thought there must be brown dwarfs around in large numbers for decades, and people had been looking for them, and no one had been finding them. One of the problems is that brown dwarfs may be substellar in mass, that is not big enough to generate energy in a sustained way.
The crucial observational determinant of a brown dwarf will be its low temperature. If we find an object that looks like a star in many ways, but has a low temperature, perhaps 1500 Kelvin, then we can be sure that it's a brown dwarf. If we look in a region where there can be only young objects, then the brown dwarf itself may be bright, may be hot. And in that case, we'll have to get the luminosity and the temperature and see where on the Hertzsprung-Russell diagram the object lies. If it lies in the theoretical region that is preserved for brown dwarfs, the region that could not be occupied by any other object, then that also would be an indication that we've captured a brown dwarf.
Observing a brown dwarf will help to further clarify our ideas about how stars form and how they change over their lifetime.
How long does a star take to go through its life cycle? Stars are a little bit different from people. That most people live, or can live if you're healthy, about the same amount of time. But for stars, it's a little bit different, because instead of taking in food from the outside, it's their own mass, it's hydrogen, which is keeping them alive.
The problem, however, is that the hydrogen will eventually run out and the gravity's just lying in wait. And so the question then becomes, what happens at that point when the hydrogen runs out?
The answer is that the core collapses. And as the core collapses, it's getting hotter and hotter. And eventually, some other reaction will turn on someplace in the star, either at the center or the hydrogen on the outside might start burning. Something's going to save it. But the core has to get hotter to turn on the next reaction, because anything involving other than hydrogen is going to need a hotter temperature to burn.
The end result is that the star is seeing much more energy flooding out from its central region than in the past, and that eventually has to work its way up to the surface. So the star itself increases in luminosity dramatically. The envelope of the star, most of the mass of the star, responds to that by saying, hey, there's something very, very hot all of a sudden in the central region that wasn't anywhere near this level before. And so the outer envelope of the star then responds to that by expanding. And as it expands, as the outer surface of this envelope, which is how far we can see into the star, cools. And so what we see from the outside is a much brighter object, a much brighter star, brightening, thousands of times over the current luminosity of the sun, and its outer surface temperature is decreasing, which drives it to higher luminosity and lower temperature on the HR diagram. And it drives it to a region which is known as the red giant area on the HR diagram.
While the transformation into a red giant marks the end of a star's term on the main sequence, not all stars complete this term in the same amount of time.
Paradoxically, the more massive stars are not the ones that live the longest. Yes, they do start with the largest amount of fuel, but they burn it up enormously fast. A massive star like the 3 stars in Orion's belt, for example, all have about 30 times as much mass as the sun does, but they are burning hundreds of thousands of times brighter than the sun is. So even though they start out with more fuel, they're going to go through it really, really fast, and they're only going to live about 1 million years or so. Whereas you take the sun, and it's going to live about 10 billion years. Stars that are smaller than the sun are going through their fuel even more slowly, and so some of them are going to last tens or even hundreds of billions of years.
Low-mass stars live a long time, and high-mass stars burn up everything and die very quickly. And so you see Every one solar mass star that there's ever been formed in the whole galaxy is still there today. But the high mass stars, you only see the ones that were formed in the last few million years. So when you start counting stars, the number of low mass stars is infinitely larger than the number of high mass stars.
There's one really direct piece of evidence that allows us to really see the consequences of stellar evolution, and that's star clusters. When we see a cluster of stars that contains a few hundred to a few thousand stars, we can assume that all of those stars formed at the same time, so they're all the same age. In an old cluster, all of the upper part of the main sequence, the more massive stars, are missing because they have died. When we see a young star cluster, we can see almost all of the main sequence, and only the very most massive stars are missing. Only the most massive stars have died. So looking at HR diagrams of star clusters, we can see immediately the consequences of stellar evolution, and you can arrange a series of HR diagrams in a string, and you can just see how the HR diagram changes as you go from young star clusters to old star clusters. So even though we only live 80 and stars live for billions of years, we can see immediately obvious evidence that the stars really are changing.